Okay, let's move on to today's topic, structural induction. So using that, we can prove this kind of thing, the rooted or binary tree, and some structural um, shape, structural set. And so in this case, we can combine them together. So induction and the recursive definition. So here we have recursive definition of rooted binary tree. So here basis is that is the rooted binary tree. That is a single node, which is root, and we have recursive step to make another binary tree. If you have two binary tree, and we can combine them together with the base, then that is again binary tree. So, and there are some functions for this rooted binary tree: size and height. Size give you number of nodes, and height give you levels. How many levels are there? And so, actually, uh, so if you move from root to another children, and then we will get this levels. So actually, if you have a single level, the height, this is the difference of the levels, so that's why if the height will be 0, like here, and size, you have single node, that will definitely 1. So if we want to know about the size of this tree, we know how many nodes here, that is 1. We don't know about this T1 and T2, so we have to find them. And for height, that's a little bit different. We know this level change, that is 1. We don't know about these and these level change. So anyway, we know about the 1 and plus other level change. T1 has some, T2 has some, but we need to know of the entire level change. So in this case, maximum one will be good for final result. And here is the structural induction itself. And so we need to prove P of X, and X is the member of S. So there is the way that there is a step for to prove something. It is similar to the induction and strong induction. We need to have base case and inductive hypothesis, inductive steps. Then we have to conclude. So first, a base case: show that P of U is true for all specific element U of S mentioned in the basis step. And then we need to set this hypothesis, assume that P is true for some arbitrary value of each of the existing named element mentioned in the recursive step. Then we have to prove uh, another thing, actually some new element from the inductive hypothesis. So we have to prove that P of W holds for each of the new element W constructed in the recursive step using the named element mentioned in the inductive hypothesis. Then we can conclude the claim is true or not. So here is the example again, the rooted binary tree. So how to apply this structural induction to prove that. So we have rooted binary tree. We want to show that is this way is true or not. The first we have to show P of W, our W, P of U. U is the dot in this case, basis, the single dot, the root node, and root node is binary tree. That's correct. And assume P is true for some arbitrary value of each of existing named element. We have two separated binary tree, T1 and T2. In this case, they are all binary tree. That's true. And next step, we want to show the new element from those trees. So we have to connect T1 and T2 using basis, the root node. So root node and T1 and T2 makes a new binary tree. That's right, this is true. So the binary tree construction is true using structural induction. So let's look at this. What is the difference between these two methods, structural induction and ordinary induction? Ordinary induction is a special case of structural induction. And I said before, structural induction is general concept of the induction. So, and structural induction follows from ordinary induction. Yeah, let's look at ordinary induction first. Ordinary induction need recursive definition of, and here we have a basis. 0 is a member of natural number because it's step. If you have a k from recursion, k from natural number set, then k plus 1 also in natural number set. Okay, what is the structural induction? Here we have, so let Q of n be true if only for all x in set S that takes n recursive steps to be constructed, P of x is true. Okay. So here is the example. So we have this case. We have two existing two bases, 6 and 15, and if we have two member of S, we can make another member of S x using x plus y. So here 6, 15, and 21, and something others. So it looks like some numbers divisible by 3. So we can prove this kind of set, a set containing numbers divisible by 3 using structural induction. Yeah, here is our claim. Let's say P of x be 3 divided x, and we prove that we the base case we know those two, 3 divided 6, 3 divided 15. Yeah, we know they are true. So suppose that P of x and P of y are true for some arbitrary x and y they are in ZS. We need to show P of x plus y. Yeah, P of x plus y. So that is coming from recursive step. So because P of x is true, 3 divided x, and so x is equal to 3m for some integer m, and P of y is also true, so 3 divided y, and y is equal to 3n for some integer n. So therefore, if you apply the x plus y, that will be 3n plus 3n, and this is will be written in this way: 3 multiply parenthesis m plus yn parenthesis, and this is a shape of multiples of 3. So that means x plus y is divisible by 3. So that means p of x plus y is true. Therefore, by the induction, 3 divides x for all x and z as is true.